In the 15th lecture, we will cover the model diagnostics. When we estimate the outcome with the linear regression model, we assume the model is correct. How do we check this assumption? Besides the commonly used measure such as R-squared, the residual plots are very useful as we discussed in lecture 13. Let's look at an example. We present two functions, f1 and f2. And for each function, both scatter plots of y versus x and the residual plots of the residuals versus the fitted values. Both f1 and f2 are regressed with simple linear models. The regression lines are displayed as the blue lines. The R-squared in the first case is below 0.5, and the R-squared in the second case is above 0.8. We may not have a clear idea of the model correctness from the scatter plots and the R-squared. The residual plots are more useful in checking the model's structure. If we look at the two residual plots, we may notice the overall residual of f1 is larger, and the residual plot of f2 has a clear curve pattern. The curve pattern is a result of the nonlinear underlying relationship. Now let's look at the two functions. f1 has an underlying linear relationship of y equal to x and a noise with a standard deviation of 0.3, while f2 has an underlying exponential relationship of y equals to ex and a noise with a standard deviation of 0.2. The lower noise level in f2 makes the R-squared in f2 much larger than the R-squared in f1. This function shows that the model in case A is correct, while the model in case B may be optimized further. We may not have the exact functions in practice, but the residual plots may give us some clues about the model correctness. We should pay attention to the pattern in the residual plots. If we observe any pattern in the residual plot, then we may need to improve the model structure. In the multiple regression, we have more than one independent variable. In addition to the plot of the residual versus the fitted values, we may also need to plot the residual versus each predictor. Also, for a specific predictor x, other predictors often affect the relationship between x and the response. Partial residual plots can help isolate the effect of the given x on y. The plot is simply ei plus xi bx versus xi, where bx is the estimated coefficient for the given x. In R, the function term plot centers the xi and the outcome called partial residuals. When we examine a linear regression model, we should first make sure the underlying relationship is linear. In regression analysis, we assume the sample is a random sample. The assumption makes sure the errors are independent and identically distributed. This assumption is violated when the errors are correlated. One common case is data collected over time. For example, the daily stock price. The serial correlation or autocorrelation occurs when the data from different time periods are correlated as repeated measures. A combination of graphical and statistical tests is available for the serial correlation. Here, as an example, we have an underlying linear relationship of y equal to x and a noise that progresses with time. The noise at time t is the noise at the previous time step t minus 1 plus a new component that follows a normal distribution with a standard deviation of 0.3. Thus, the errors are correlated. The residual plot against the time step has a pattern with long sequences of points as an indication of serial correlation. Also, we may plot successive pairs of residuals as in the second graph. The positive correlation is again a clear indication of serial correlation. In the Durbin-Watson test, the residual ET is this. The null hypothesis is rho is 0, and the alternative hypothesis is rho is not equal to 0. The test statistic dW is this, approximately normal for large sample size. In this example, we have the test statistic dW is 0.154 and a very small p-value close to 0, indicating a very strong first-order serial correlation. Serial correlation can also be caused by a missing covariate if the omitted variable has the serial correlation. Thus, it may be improved by optimizing the model structure. After we make sure that the model is sound, we need to check if the data are correlated. If they are strongly correlated, then we need to build the correlation into the model. The residual plots are also useful for checking the constant variance assumption. When the error term is related to the independent variables, we have non-constant variance or heteroscedasticity. Here we have 4 cases. In case A, the error follows a normal distribution with a standard deviation of 0.3. The residual plot has no clear pattern and no evidence of heteroscedasticity issue from the plot. In case B, the error standard deviation is weakly dependent on x with 0.3 plus square root of x. The residual plot shows the residual has an overall smaller variance when x is small. In case C, the error standard deviation is 0.3 plus x. The trend that the residuals increase with x is more obvious in the residual plot. In case D, the error standard deviation is 0.3 plus x squared. The residual plot shows strong heteroscedasticity. The residual plots are very effective at detecting non-constant variance, but it leaves certain ambiguity, especially when the noise is large and the dependence is weak. We may also combine some statistical tests to check non-constant variance. The Breusch-Pagan test, also known as Cook-Weisberg score test, is a chi-square test for checking non-constant variance in a linear model. it assumes that the error is normally distributed and the residuals are linear with x. We first regress y on x and then use the squared residuals as the outcome to regress again on the same predictors. The parameter provides a measure of the linear dependency of the error term on x. The test statistic follows a chi-square distribution with p degrees of freedom. Here, RSS0 is the residual sum of squares in the first regression model, y versus x, and the ESS is the explained sum of squares in the second regression model. A variant of the test uses the n times r squared from the second regression model as the statistic. If the test statistic has a p-value less than alpha, then the null hypothesis of constant variance is rejected. For example, the test statistic in case A is 0.022 and the p-value is 0.88. We find no evidence to reject the null hypothesis. But for the case B, C, and D, we find evidences to reject the null and suggest non-constant variance in these cases. Also, we assume the error is normally distributed. We may use Quantile-Quantile plots known as QQ plots to check the normality. Histograms may not be suitable because they could be affected by binning. Now, we use a sample of 9 to show how to draw a QQ plot. First, arrange the data from the smallest to the largest. Here, D1 is the smallest and D9 is the largest. Evenly divide the distribution into n plus areas. Since the sample size is 9, here we evenly divide the distribution into 10 areas and calculate the z-scores for each segment. For example, the first segment has an area of 10% and the z-score is minus 1.28. Use the z-score as x-axis and the data as y-axis. We have a QQ plot. The sorted data are compared with the ideal straight line to detect the non-normality. On the right, we have two QQ plots based on the two cases discussed earlier. In case A, F1 has an underlying relationship y equal to x and a noise normally distributed with a standard deviation of 0.3. In case B, F2 has an underlying relationship y equal to exponential of x and a noise with a standard deviation of 0.2. We do not observe any clear trend that the curves deviate from the straight line in both plots. It is not always easy to diagnose the non-normality in QQ plots. We may also use some statistical tests to check the normality. One popular normality test is the Shapiro-Wilk test. The null hypothesis is the sample comes from a normally distributed population. The test statistic is this, with yi is the ith order statistic, which is the ith smallest number in the sample. The statistic does not have a specific distribution form, and we may determine the p-value numerically. The test lacks power for small samples, while for large samples it is very sensitive and may reject the null hypothesis for mild non-normality. SAS uses the Shapiro-Wilk test only when the sample size is not larger than 2000 in the capability procedure. There are other tests available to check the normality, such as KS test, AD test, etc. We recommend these tests in conjunction with the QQ plots. Also, when the sample size is sufficiently large, we can appeal to the central limit theorem to ensure the inference is approximately accurate and ignore the issue. Practically, we may think the sample is sufficiently large if the sample size is larger than 30 plus 10 times p, where p is the number of predictors. The discussed linear regression assumptions should be checked in order according to their importance. The model structure should be the first to check. If the model structure is wrong, then the inference will be inaccurate. There are two possible reasons in the linear regression that may violate this assumption. The underlying relationship is not linear, and or the model didn't include all important predictors. In practice, a low R-squared is certainly the first warning sign of a poor model for an investigation on the model structure. The error independence is the next one to check. If the errors are strongly dependent, then the efficiency will be affected. For example, the model may underestimate the standard errors for a positive serial correlation. The third is the constant variance assumption. In practice, non-constant variance is a concern when we find an obvious trend that the variance changes with x from the residual plots. The inference may still be adequate if only mild dependence on x is found. The last one is the normality assumption. The inference is robust to a lack of normality for large samples. Unless the sample size is small and the errors deviate much from a normal distribution, this assumption may not be crucial. In summary, we discussed the model diagnostics in the lecture. First, we check if the model structure is reasonable and correct. Besides the R-squared values, we may also check if there are patterns in the residual plots. The error independence should be the next one to check. For example, serial correlation or autocorrelation occurs when the data from different time are correlated. The Durbin-Watson test may be used to check the serial correlation. The residual plots as well as the Breusch-Pagan test may be used to check the constant variance assumption. The QQ plots and the statistical tests such as Shapiro-Wilk test can be used to check the normality. The inference is robust to a lack of normality for large samples, unless the sample size is small and the errors deviate much from a normal distribution. The assumption may not be crucial.